Welcome back. I want to finish up our first half focused on variational autoencoders by talking about some of the state-of-the-art variational autoencoders that are available. We've really just scratched the surface of this class of models. And this is one of the powerful aspects of working with deep learning-based tools, which is that you have a lot of room for design creativity based on the problem space you're working on. So here's the basic structure of our variational autoencoder again. And it turns out that there are many opportunities to modify aspects of this architecture to better suit problems that you're trying to solve. One big area of possible improvement is the use of parameter sharing. And you've already seen this with the convolutional autoencoder and convolutional variational autoencoder that you've used in the tutorial. So specifically there, you're using a convolutional neural network to better represent image data. But the same idea can be applied to time series-like data and is often done by using recurrent neural networks. Variational autoencoders and autoencoders can be modified with respect to the objective function. As we've talked about, those objective functions can be modified to better align to the goals of the problem. There are objective functions that better match human perception for audio, for vision, for example, than a least squared estimator. We can also change our definition of the latent space to better represent the problem at hand. So you guys have already seen this example of parameter sharing with respect to the convolutional neural network for image processing. But the same idea can be applied to time series data. And here's an example of what's known as a seek-to-seek autoencoder. You can also create a seek-to-seek variational autoencoder. And the basic idea is that we have a time series that's an input. That time series has some length n, and it gets encoded by a recurrent neural network like an LSTM or a GRU. And the final output of that recurrent neural network is the input for Z. So we take that final output, we get our estimate of our latent variable or our distribution in the case of variational autoencoder. And then we take either that value or we sample from that distribution for the latent variable. And that's the input for a decoder recurrent neural network. And the goal is to reconstruct the time series that was the input to the encoder, just like any other autoencoder or variational autoencoder. And so this gives us a way to share parameters across time for time series data and can be very effective. Now, if we expect the latent representation to be discrete, there is a modification of a VAE that's called a vector quantized variational autoencoder. And what this does is it discretizes the latent space. So for example, if we have human speech is composed of underlying phonemes. And so we might want to motivate a latent representation that has a discrete representation similar to the symbolic phonemes that form human speech. What the VQ-VAE does is it introduces a codebook. And so that codebook replaces the continuous valued latent representation with a nearest neighbor in that discrete codebook. And this has been a very effective technique for a number of problems, including the development of latent representations for human speech. We can also modify the objective function. So the beta VAE is a state-of-the-art technique that directly modifies the VAE objective function. Now there are different forms of disentangled VAEs that are a little more complicated than the beta VAE, but I'm bringing it up here because this one's very simple to introduce. And you'll get an idea of why this disentangled VAE exists. So recall that when we upgraded from the autoencoder to the VAE, we got this encoder objective. And what this encoder objective did was it put some pressure on the latent space to be concentrated close to 0, so that we have a more compact latent representation of all of the data that was used to train the model. Now, what the beta VAE does is it simply upweights that encoder objective. So we're going to modify this objective to emphasize the encoder objective. And the reason this is done is that the goal is to disentangle the latent space. So by making the latent space more compact, we're putting pressure on the latent space to better represent the range of possible input data. And the modification algorithmically is actually quite simple. What we do is we weight the encoder objective. For the original VAE, the weight is 1. For the beta VAE, we increase the weight of the encoder objective. And the actual weight can be found either by experimentation or by using model selection techniques. But the basic idea is that we're upweighting this encoder objective. And to provide some motivation as to why this technique is useful, let's look at an example. So using a celebrity face data set, we can train a VAE, and then within that VAE, we have a latent space. In that latent space, we can find the latent direction that best aligns to the angle of the head, right? So if we have some additional data about the angle that the head is at each image, we can find the direction that best describes head angle. And then we can generate images along that direction. So we can start at different points in the latent space and move along that direction. And ideally, what we would see is that as we move along, we'll simply see the head shifting its direction. And that's what's done on each of these rows. Each of these rows starts at one point in the latent space and moves in the best aligned direction to head angle. And as you can see, in general, yeah, the head angle is changing, but other characteristics of the face are changing. You can see this very clearly in the middle row, where the image all the way to the left has no sunglasses, and the image all the way to the right has sunglasses, right? So that's a change other than head angle. Now, if we introduce the beta VAE, we upweight that encoder objective, what we find is a representation that is better aligned to that single goal. So here we take that beta VAE, it's going to have a different latent space than the VAE, but again, we find the direction that best aligns to head angle, and we choose an initial sample and then move along that direction and along that axis in the latent space. And I would argue that the beta VAE examples have much more consistency in terms of the face that's being shown, and we see a more consistent change in head angle. Now, neither model is perfect, so you can see in the first row of the beta VAE that the hair color is changing quite a bit between the angles, but the faces, I'd argue, are much more consistent than the faces that we're seeing in the regular VAE. And this improvement is simply due to the upweighting of the encoder objective. So that ends our section on autoencoders and variational autoencoders. So you're going to move onwards now with Akash to learn about generative adversarial networks. These give us another powerful way to develop meaningful and reusable latent spaces.